Good morning, students. Last class we discussed about the production of RMF and also principle of operation of three-phase induction motor. Those three topics are very important. That is construction, difference between spiral gauge spring, then principle of operation of three-phase induction motor, and also sometimes they are asking RMF also, production of RMF also. Now go for the another topic of a three-phase induction motor, that is equal to the slip and effect of slip on different parameters, and also torque equation. Slip, what is meant by slip is nothing but, so before we going to the slip, first of all we have to discuss about the slip speed. What is the slip speed? Slip speed is defined as the difference between the synchronous speed and actual speed of the motor. Slip speed is nothing but difference between the actual synchronous speed and actual speed. That is ns minus n is nothing but slip speed. Now what about slip? Slip is defined as the difference between the synchronous speed and actual speed, and it is expressed as the synchronous speed. So slip of a three-phase induction motor can be defined as the difference between the synchronous speed and rotor speed, and it is expressed as a function of synchronous speed. So slip S is equal to synchronous speed minus rotor speed by synchronous speed, that is equal to ns minus nr by ns. In slip in percentage, S in percentage, ns minus nr by ns into 100. So now from that equation, rotor speed is equal to nr is equal to ns into 1 minus s rpm, right? nr is equal to ns into 1 minus s rpm. And now synchronous speed, where ns is equal to 120 f by p rpm. So practically at no load the value of slip may be 1 to 2%, and at running conditions the slip may be increased 4 to 6%. At no load condition, slip maybe have 1 to 2% only, but at running condition slip is 4 to 6%. Generally, how can you derive this one? S is equal to ns minus nr by ns. So that is equal to nr is equal to ns minus s ns. Therefore, nr is equal to ns into 1 minus s rpm. From that equation, nr is equal to ns into 1 minus s rpm, right? From the above equation, the relative speed or slip speed of the rotor and the rotating magnetic field is directly proportional to the slip. That means it is directly proportional to the slip. At starting, that is n is equal to 0. At starting, nr is equal to 0 or n is equal to 0. What about slip? ns minus 0 by ns by ns, that is equal to 1. At no load condition, the slip is equal to 1, that is the maximum value. So maximum value of slip for three-phase induction motor is 1. Minimum value of slip for three-phase induction motor is 0. Suppose at rated condition, that is n is equal to ns, nr is equal to ns. What is the slip? ns minus ns by ns, that is 0. Slip is 0. Now range of slip. What is the range of slip of three-phase induction motor? Minimum value is 0, maximum value is 1. For three-phase induction motor only. Suppose three-phase generator, that will be different. So braking condition, that will be different. For three-phase induction motor, n is equal to 0, n is equal to 1. So at 0 is nothing but, so it is no load full load condition. So 1 is nothing but at no load condition. Now, effect of slip. Effect of slip on different rotor parameters. So first of all, go for the rotor frequency. The relation between the synchronous speed and supply frequency and the number of stator poles, ns is equal to 120 f by p. So the relation between the synchronous speed, number of poles and rotor frequency is nothing but ns is equal to 120 f by p rpm. From that F is equal to NSP by 120 heads. F is equal to NSP by 120. When the rotor rotates its speed NR, then the rotor conductor cuts the RMF at a relative speed ns minus nr. Now the rotor speed can be expressed as ns minus nr by 120 into p head. By f, fr by f, fr by f, ns minus nr by p 120 divided by, so f is nothing but p ns by 120. Now ns minus nr by ns, fr by f is equal to ns minus nr by ns. So this is look like as a slip. Therefore fr is equal to s into f heads. Rotor frequency is equal to stator frequency into slip. Hence rotor frequency is a running condition is slip times of the stator frequency or supply frequency. At the starting s is equal to 1. At starting s is equal to 1. Therefore fr is equal to f. So at starting both rotor frequency and stator frequency must be equal. Next parameter rotor resistance and also rotor induced EMF. Now I am first go to the rotor induced EMF. When the rotor is stationary, standstill is nothing but slip is equal to 1. The EMF induced in the rotor is maximum. This is due to the rate of cutting of flux by rotating magnetic. Rotor is maximum as the rotor speed means the resultant speed decreases and rotor speed increases. Now look at the E2R is equal to S into slip times of the secondary stator EMF. At standstill S is equal to 1, therefore E2R is equal to E2S. Under running condition E2R is directly proportional to NS minus NR, therefore E2R by E2 is equal to NS minus NR by NS, that is equal to slip times. So E2R is equal to slip times of the stator. Rotor induced EMF on running condition is slip times of the stator induced EMF. Similarly, rotor resistance and rotor reactance. Right? Rotor reactance is equal to 2 pi f L2. Reactance under running condition 2 pi fr L2, but fr is nothing but SF. So 2 pi s f L2, that is s into 2 pi f L2, s into x2s. Rotor reactance under running condition is equal to stator reactance multiplied with slip. Next, rotor current and rotor power factor. We know that current per phase under running condition is I2R is equal to Z2R by E2R. Sorry. Rotor current per phase under running condition is equal to I2R is equal to E2R by Z2R. We know that E2R rotor induced EMF is equal to slip times of the stator induced EMF. That is E2R, in place of E2R you have to put S into E2S. Divided by Z is nothing but combination of resistance and reactance of rotor, that is R2S square plus S X2S square. Suppose at standstill S is equal to 1. So X2S is equal to 2 pi of L2. Z2S is equal to R2S square plus X2S square whole root. Rotor current for phase E2S by Z2S, that is equal to E2S by square root of R2S square plus X2S square. Power factor is nothing but R by Z. R2S by Z is nothing but square root of R2 square plus X2 square. This is the rotor current and also rotor power factor. Now the torque equation of a three-phase induction motor. Torque equation of a three-phase induction motor. So let us consider a three-phase AC supply is given to the stator. It may develop rotating magnetic field. That rotating magnetic field may interact with the rotor, then it will develop the torque equation. Torque. Because of the torque, motor will be rotating with some speed. Now torque is directly proportional to of a three-phase induction motor is directly proportional to the flux, that is stator flux, and also current in the rotor and the power factor in the rotor. Stator speed ns is equal to 120 f by p. Cos pi 2r is equal to rotor power factor under running condition. Cos pi 2r is equal to rotor power factor under running condition. That is r by r2 z by z r2s by z2r, that is equal to r2s by square root of r2s square plus sx2s whole square. Now torque is directly proportional to flux, rotor current, rotor power factor. We know the rotor current, we know the rotor power factor. So torque developed under running condition T is equal to K into pi I2R cos pi 2R, where K is equal to 3 by 2 pi ns, because it is three-phase motor. Therefore torque is equal to 3 by 2 pi ns pi into SE2 by R2 square by SX2 square into R2S by square root of R2 square plus SX2S whole square. That means T is equal to 3 by 2 pi ns E2S into S E2 R2 E2S R2S by R2S square plus SX2 square. So this is the torque equation. Now at full load condition or running load condition S is equal to 1. So that is equal to 3 by 2 pi ns S E2 square by R2 by R2S square plus SX2 square Newton meter. So getting the condition for maximum efficiency, that is R2 is equal to SX2, R2 is equal to SX2. The torque is maximum when the standstill rotor resistance. Next, go for the another important term. Condition for maximum torque and equation of a maximum torque of a three-phase induction motor. You know the full load torque 3 by 2 pi ns S E2 square R2 by R2 square plus SX2 square. To get the condition for maximum efficiency, maximum torque, differentiate the above equation with respect to slip equating to 0. Then we are getting R2 is equal to SX2, that is SM is equal to R2 by X2. Now I have to explain the torque slip characteristics. So it consists of three regions. One is low slip region, another one is medium slip region, another one is high slip region. So these three regions also torque proportional to slip, torque inversely proportional to slip. And the curve obtained by plotting the torque against slip is called torque slip characteristics. So of a three-phase induction motor. The curve obtained by the plotting the torque against slip is called torque slip characteristics of a three-phase induction motor. We know the expression for the torque is T full load is equal to 3 by 2 pi ns S E2 square R2 by R2 square plus SH2 square Newton meter. Now we have to observe the torque slip characteristics. When the rotor speed is equal to synchronous speed, that is ns is equal to nr. ns is equal to nr. The slip is 0. Then the torque is also 0 from equation 1. So Whenever slip is 0, torque is also 0. When the load on the motor is increases, the speed decreases and slip increases. The value of Sx2 is very small compared to R2 and neglected for constant rotor EMF V2. Now torque is equal to K into S R2 square by R2 square, that is square and R2 square cancel to each other. So torque is directly proportional to slip. So that means torque slip characteristics is divided into three regions: low slip region, medium slip region, high slip region. For low slip region, so Sx2 will be neglected. That means R2 square, R2s square is remaining. Therefore, torque is directly proportional to slip, and this curve is a linear curve, straight line. Next one, medium slip region. As the load increases further, the speed decreases and slip also increases. The resultant in increase in torque and reaches the maximum value. High slip is equal to R2s by X2s. When the increase in load beyond the maximum torque, the slip increases further. Now the value of Sx2 is more compared to R2R. Therefore, R2 is neglected. Therefore, torque K is equal to S by S square X2S square. Therefore, torque is proportional to 1 by S. Now I have to go. Torque is proportional to 1 by S for medium slip regions. That means hyperbolic curve. The curve is hyperbolic curve. Look at the picture. From S is equal to 0 to this one, it is a linear curve. And then this is a hyperbolic curve. S is equal to 0 to S is equal to minus infinity. I mean S is equal to 0 to S is equal to 1. So torque slip characteristics very important. Three regions: slip is equal to low slip region, medium slip region, high slip region. Low slip region S is equal to 0. Medium slip, high slip, low slip region, the curve is directly, the torque is directly proportional to the slip. That is a linear curve. So now the load is again increases, the slip value increases. That means torque is inversely proportional to slip. So it is a rectangular hyperbola. For medium and high slip, torque is inversely proportional to the slip. For low slip, torque is proportional to the slip. Thank you. These two topics, that is torque equation and slip torque characteristics, very important. On slip, rotor frequency, rotor current, rotor induced EMF, those parameters are important for 2 marks. And problem must be asking on that concept only. Slip, rotor current, rotor induced EMF, torque, maximum torque, so starting torque, like that they asking. So last class, in this unit, last class I discussed about the problems. So next class we discuss about the efficiency losses of a 3-phase induction motor, relation between the copper loss, input and mechanical output. So that is S in 1 is to S is to 1 minus S. Also you have to derive. Thank you. To see this video, please subscribe DBS Talks. Thank you once again.